What's up everyone? So today we're going to start another problem, a very common problem in recursion, and it's called nqueens. So the problem basically goes like this: you're given an n by n board. How many different ways can you place n number of queens so that they don't attack each other? And people familiar with chess would know that a queen can move vertically up, down, it can go horizontally left, right, and it can go diagonally. So it's like a rook with some diagonal leeway. Probably the strongest piece on a chessboard, you would say. Now before we get started, I got some feedback from some of my friends. Shout out to Sangeet Satish from Trivandrum, Kerala, who said I should be smiling more. So today's session is going to be more about me smiling. Thank you, Sangeet. Moving on. So for this example, let's start with an example where you have n is equal to 4, which basically means that you have a 4 by 4 chessboard, and you're given you're thrown four queens, and the question is, okay, how many different ways can you put this there on the board, and also tell me where I had to place it on the board. Now for this particular example, there's only two ways to do it. So if you look here, these queens don't attack each other and these queens don't attack each other. Now one thing that we will use as a notation for this example is that our rows are going to be numbered from 0 to n minus 1, and our rows are going to be from 0 to n minus 1. So this is a recursive question. This is also a backtracking question. The reason why it's a backtracking question is that you want to go through each and every possible solution, right? So let's have let's have a third box. I notice in some of the videos online, people start drawing the boxes without knowing how many boxes you need, and they end up doing an extra one. So I always start from the middle and then divide it by 2. I think it's some sort of a binary division, but anyway, it works for me. It probably wouldn't work if it wasn't multiple of 2. Yeah, you're right. That's probably why. If there was 5, then you have no other option, right? Moving on. Let's say that you are going to... So what's the basis of recursion? A recursion function has to go through each and every single possibility, right? That's just how recursion works, and we are basically forcing the computer to do all that work for us. So every time you select a position, you need to go and check, okay, is this position good? And if it's good, yeah, keep going down that path, right? If it's not good, remove that. Okay, even if it's not good, it doesn't matter. You still have to go through the other options, right? So that's why we say, okay, let's say we start with Q in that position. Queen is in the first column on the in the 0th column, in the 0th row. Now you could go through all of these chains going down, 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 but eventually, because I know the solution for this, you're not going to get an answer here, right? So you're going to come back, and then you're going to remove the fact that queen was placed there, and then you're going to go into the next one, and you're going to do Q and place Q there. So now the recursive part of this code comes in, where you have to go through every row. You have to check, can I put it in column 0? Can I put it in column 1? Can I put it in column n minus 1? So you have to go through every possibility and check if that's a valid possibility. And I create this vector called a temporary or a partial vector. I call it the partial vector. And what I put in the partial vector is the values or the column numbers for my partial solution. So for example, if I'm at row number 0, okay, if I'm at row number 0, then I would put in row number 0, if I was at column number 3, then I put the value 3 in there, and then at that point my vector would just have 3 because I've only gone through one of the rows, row 0. So every time I go through this, I have to push back a value into the vector. So I'm going to do that here. I'm going to say partial dot push back. I'm going to push back. What are you going to push back? Current column. Okay, that's because I want to check for that, right? And then let's say there's going to be a check here. Come back to that in just a moment. And then what do we want to do? We might or may not find some solution down there, but even if we did find a solution, or we didn't find a solution, we still have to go back, clear it up, and start again, right? Otherwise, when you come back, you wouldn't know. Okay, let's see what happens if you didn't do that. Let's say that you forgot to do this, and in the first case you pushed 0 into the column, right? And then you go into the recursive function. Let's assume that you don't have this part here, so that 0 stays there, right? So in your final answer, your vector is going to be larger than 4 or n, right? Your vector is going to keep growing and growing, and you have no idea which element in the vector corresponds to which row. So that's why we always say that. So if you have these values, so let's put in these values, the actual result values. So this would be 1, 3, 0, and 2, right? Because we have 4, we know that this points to row 0, this points to row 1, this points to row 2, this points to row 3. And that's the whole idea of having the pop back. And this is where your backtracking is going on, right? Do we want to go back and see something else? Yeah, that's exactly what's happening here. Now, quickly moving on to the check part, okay? What are we going to do? We're going to do if is a valid, if our partial is a valid partial, then what do we do? We're going to keep going down the recursive stack, right? What are we going to do? We're going to call, like, let's say our helper function, which is basically this function called again. I'm going to call the helper function, and what are we going to pass? Well, for one, we'll have to pass how big our chessboard is. We'll have to pass what row we are at right now. Now, since we've already we think we've found a good candidate, we're going to use that value, and then we're going to move into the next row, right? So row plus 1, we're going to send in the partial, and we're going to have a result array. Now the result array will be all of the solutions, right? So at some point partial will get filled with 4 values, and then we're going to push that into the result. So now those parts are kind of easy to understand. Let me actually tell you about the base condition. So when do we terminate this recursive helper function? We're going to terminate it when the value of row exceeds the limits, right? So row starts from 0, 1, 2, 3 for this example, and then when it goes to 4, you're going to say, oh, okay, stop. We've already reached 4 and we found a possible solution. So let's put that value into result. And then we just return. Okay, so that's the base case. Now, the interesting part of this problem, and where the heart or the crux of this problem lies, the beauty of this problem lies, is how do you find out if a current position that you've taken is actually valid, right? That's the hidden question here, because everything else is like, yeah, it's backtracking. Yeah, I select a value. Is it a good value? Okay, keep going down. Is it a bad value? Okay, come back up. How do you check for that? Now, let's have some bad examples, okay? I want to have some really bad examples, okay? Let's say that in the first row, we selected Q to be in the 0th column, okay? And then we're good, we keep going down, and so far there's nobody else on the board, so that could be a valid situation, right? Now let's come down and let's say that even for row 1, I want Q to be in column 0. Now, is that possible? No. So how would you check that? So you would have to iterate through all of the previous guides, right? So for row equal to 0 to row less than row ID, row plus plus. So what do I mean by row ID is the maximum number of solutions that we have right now, or the number of the row that we are working on right now. So we have a candidate for this particular row. So let's say in this example we are at row 1 and we have a possible candidate, right? We want to check if he is possible. So we will go starting from the first and then keep coming back. So in this case we'd start from 0. We just have one person to compare against, right? So what we're going to check for is a beautiful thing. We're going to find out the absolute value of your partial vectors row value and partial of row ID. Okay, now give me the values here. So let's not put it there, let's put it somewhere else, right? Let's say that you selected Q and Q, these two places. Okay, now what's the column number there? So the partial of row would be, so it's 0, so it's 3, and here it would be 3. So if you have a case where the difference, so basically how do you do this? If they're both equal, that's what you're checking for. But the reason why we're using this value is that we can use it to use it for our diagonal as well, right? Diagonal problems, can we solve that problem as well? So if you do 3 minus 3, it's 0. That means that you cannot have a solution there. Now coming into the diagonal part, this is where it gets really interesting, and this is where you need to have a lot of clarity in the solution. Okay, so let's say we have Q here and we have a Q here. Okay, now when he compares his partial row, so that the value is, what's the value here? This will be 2. Sorry, that'll be 1, and this will be 2. So 1 minus 2, the absolute value would be 1, right? Now you're going to check if the current row that you're checking for and the current row that you are previously looking for, if the difference is equal to this difference, that means that you have a possible a diagonal, not a possible, it is a diagonal. So let's look at the value. So right now your row ID, or the row where you have a possible new candidate, is going to be 2, and the position where this guy is sitting at is 1. So when you do 2 minus 1, that's 1. hey, we found. I'm going to make my arms a little bit just for Sangeet. So they're both equal, right? And because they're equal, you're fucked. You can't use that. Now, this would also work. Now you tell me, hey Atul, the the diagonal doesn't even have to be immediately next to me. It can also be somewhere far away, right? Let's say we put our Q here. Now even here the same math would work. There's no problem. It would still work. Now let's say we put the queen over here. Now let's look at our values. What's our partial of rho? The value would be 0. And what's the partial of rho ID is still 2. So what's the difference? The difference will be 2. Now what we're going to do is we're going to check the row ID is 2, and then we're going to check what row we're comparing against, right? So that's also going to be 2 minus 0, which is 2. And now, fucker, you've again found another diagonal, so you can't go down that path. So that's how you check for whether this is a valid possibility for keeping the queen there or not. Anyway, that's the nqueens problem. I will post a solution from EPI as well as a simplified version of the EPI code, because they're using some unique stuff, and they're overusing some pointers which we don't really need for the solution. Now, there could be cases where you would have to actually print this out, but that's a trivial thing to do. You could be asked a similar question based on number, the keypad, and you have a horse that's allowed to go through the keypad, and all possible combinations of that. That's also another backtracking problem. But yeah, this is a very interesting problem. I hope you had fun, and I'm going to leave you with a fucking smile. Hey everyone, if you like the video, please make sure to like, subscribe and share. There's also a GoFundMe page where you can go and fund my wife's dental school, and I would like it if you would donate anything, $1